My name is Keita Arimoto from Yamaha, Japan. I'm going to present my work with the title Identification of Drum Overhead Microphone Tracks in Multi-Track Recordings. Let me start my presentation with background. These days, it gets quite common that musicians share multi-track recordings over internet. This is thanks to fast network and huge storage, and this results in bringing a new paradigm for music creation, like promoting reuse of musical materials as well as remix. On the other hand, there may be no objection to say that musical instrument level is one of the most basic and important metadata for multi-track recordings. And the musical instrument level is usually found at the track level of DAW software in most cases, but it's not always the case. This is a typical example. The track level is shown to be the name of players instead of instrument level. But it's somehow easier to manage tracks at recording studio, and this is likely to happen. So we need an automatic musical instrument level system by contents analysis. So the goal of my project is building such an automatic system that takes multi-track audio as an input, and then the system comes up with track levels like kick, snare, tom, bass, guitar, blah, blah, blah. This may help you in saving time to take a listen to individual tracks and giving track levels. And there are some studies that are expected to be applicable for that purpose. For example, there are some studies on musical instrument identification. And the concept is applicable as long as the track is catching a specific target source. I mean, you can see some tracks that are marked with orange square. For example, kick, snare, toms, bass, guitar, vocal, blah, blah, blah. All of them are catching a specific target source, so the audio signal in the track are quite consistent. For such a signal, the concept of musical instrument identification may be applicable, but it's not the case for drum overhead. This is a typical microphone arrangement at recording drum performance. There are some microphones dedicated to specific sources like bass drum or snare drum, but overhead is completely for different purpose. Overhead catches entire drum set instead of a specific sources. So the observation may be a mixture of drum sounds. In order to have an identification for such overhead tracks, we need a completely different concept with the other tracks. And one possible option toward building such an automatic system for overhead identification is extending the concept of polyphonic drum transcription. There are some works on this direction, but I personally think that this is not a good option, as such a system usually depends on models or knowledge for drum sounds, but drum sounds differs from players to players and genres to genres and drums to drummers. So I think it's not a good approach. On the other hand, Rona et al. Tried automatic subgrouping of multi-track recordings, including drum overhead, but they were not directly addressing to the identification of individual tracks. And another relevant work is done by Scott et al. They tried 4-class drum sound classification, including overhead, but there were only 4 classes and drums only, so it's hard to expect that this is directly applicable for real multi-track recordings that includes not only drums, but also vocal, guitar, bass, blah, blah, blah. So as a conclusion, I think there's almost no works directly applicable for the identification of drum overhead, and this is a fatally missing piece toward building such an automatic labeling system. That's the motivation of my work. Okay, let me go to my system. I built my system based on the concept listed here. First, my system doesn't depend on any models or knowledge for drum sound. The only requirement is a general classifier for percussive sound and non-percussive sound. And I built my system based on the A to C characteristics that are listed here, and they are commonly observed in drum overhead. A more onset than the other drum tracks. This is quite reasonable as it catches the entire drum set instead of a specific source. And this is evaluated by a measure that is called onset rate in my study. B, catch more percussive sound than non-percussive sound. Even if there are some interferences coming from non-percussive sources, but still drum overhead is expected to capture more percussive sound. And this is evaluated by a measure that is called percussiveness in my study. And the last one, high onset-offset coincidence with the other drum tracks. If a drum is uttered, then the sound is caught by a dedicated microphone close to it, as well as overhead. This results in overhead having high onset coincidence with the other drum tracks. This is evaluated by inter-track onset coincidence in my study. Okay, based on the concept listed here, I built my system. On the left, you can see audio signals, each of which are corresponding to tracks in multi-track recordings. And the result is obtained for each track if the tracks are overhead or not. Okay, let me explain step by step. All the audio signals are first applied with onset-offset detection as a first step. This is quite simple envelope-based method and nothing special, so let me skip the details. And once onset and offset are detected, then feature extraction is performed for each pair of onset and offset. The audio signal between onset and offset is sliced into frames, and MFCC is computed for each frame. And then the frame-wise MFCC vectors are finally summarized into total 65-dimensional feature set for a pair of onset and offset. The first one is the MFCC average over frames, and the second one is the MFCC variance over frames. And the last one is better to be explained by the next slide. To begin with the concept or purpose, this aims to capture the temporal behavior of the timbre in the vicinity of attack. So horizontal axis is corresponding to frames, and the vertical axis is corresponding to MFCC dimension. And what I did is computing DCT against each MFCC dimension, and to take out initial 3 DCT coefficients as a feature. This is expected to capture the temporal change of each MFCC dimension. And the idea comes from the work done by Maxwell et al. Okay, let me go to SBM classifier. The SBM classifier is to have a binary classification between percussive sound and non-percussive sound. And the training is done beforehand using 3626 instances. And all the training data come from completely different context with the one that was used for experiment. And the training achieved 96.73% average accuracy in F measure. Okay, let me go to the 3 criteria that are corresponding to A to C characteristics that I explained in the concept slide. First one is onset rate. This is given by the definition. Number of onset in a track S is normalized by that of the track having the most onsets. So this gives 0 to 1 measure corresponding to the number of onset in a track. And the next one is percussiveness. I think the diagram helps you to understand what is the percussiveness. Imagine that you have 1, 2, 3, 4, 5, 6, 7 percussive onsets, and the rest of yellows are non-percussive. In this case, the percussiveness for this track is given to be 0.7. In this way, this also gives 0 to 1 measure for the percussiveness of the track. And the next one is inter-track concept coincidence. Actually, this is the heart of my system, but as I put the details in my poster, so if you are interested in the details, please visit my poster. Please ask me the details. So let me here explain the, concept of it. The concept is evaluating overlap of onset-offset regions among tracks. So imagine that you have a track S that is a source and T that is a target, and each of which has a series of onset-offset pairs over time. And what I did is computing overlap between these 2 tracks, and I get this DST. Then after getting this, I do some refinement by applying 1-by-1 pairing, and then I got this D tilde ST shown at the bottom. You can see that small overlap shown here is not shown at the bottom. This is thanks to 1-by-1 pairing. In this way, I got the overlap between tracks, and this computation is repeated for all the rest of tracks. And finally, this is reduced into a measure that gets higher value if a track has a more coincidence with the other tracks. Okay, now we got 3 criteria, and so final decision is made by a simple threshold for all the 3 criteria. If a track is identified to be overhead if all the 3 criteria get more than the thresholds. Okay, let me go to experiment. I conducted my experiment using 21 multitrack recordings that come from open multitrack testbed, and I made full use of all the recordings in WAV format, and that includes at least an overhead track. And all the data was converted into 12 kilohertz 8-bit format. And before running experiment, I picked out some confusing tracks like ambience or polyphonic drums. So then finally, I got 42 tracks for overhead and 58 tracks for the rest. And the results in recall get 95.23% for overhead and 92.14% for the rest. Note that precision of F measure does not make sense in this case, as the definition assumes positive and negative instances are equally balanced in the test dataset. But in my case, it's not the case, as the ratio is 42 and 458. Let me talk some about the erroneous cases in the rest group. Most of them are occupied by snare and hi-hat. For the case of snare, the observation at overhead sometimes gets closer to the observation at snare depending on microphone arrangement and phrases. And for the case of hi-hat, as hi-hat is usually located close to snare drum, so the observation at hi-hat is likely to get a mixture of hi-hat sound and snare sound. That results in getting close to the observation at overhead. This seems to be the reason. So let me wrap up. As a conclusion, I built a system that automatically identifies drum overhead microphone tracks out of multi-track recordings. And the result is quite satisfactory as a first step, but there's a room for improvement. One thing I have to do is dealing with the case that there's no overhead in multi-track recordings. This is because current system assumes that there is at least an overhead. But of course, there are many multi-tracks that doesn't have any overhead nor drum tracks, so this is one thing to be done. And this time, I made final decision using simple threshold for 3 criteria. But I think it's better to be replaced with machine learning if I get more data enough to train machine learning. And in this study, I picked out some confusing tracks like room or polyphonic drum tracks, but I think it's better to be able to deal with the case that such a tracks are also lying in the merge track as well as drum overhead. So that's it. Thank you for listening. And any questions?